that we have the CSSP on site. I will come to that later, and the Forschungszentrum Borstel has now joined the CSSP as a 10th partner. Helmut was mentioning already Leap spin-off, so there was a kickoff meeting, and I don't have to tell you more about that. And we also had a quite successful summer student program. Unfortunately, most of those people, as you can see here, no group photos, but these screenshots were only participating in remote, but this is also very good for young people to get acquainted with us. Helmut mentioned the 2 prizes, which we are proud that our ladies are so successful in to achieve these prizes. We are quite successful together with colleagues from KFS and the community to attract quite substantial partner funding for the national science data infrastructure in Germany. And this will certainly help us to deal with the data deluge that we've encountered at our facilities. And I told you last year we had that we were together with Helmholtz-Zentrum Berlin and Helmholtz-Zentrum Dresden-Rossendorf. We're writing up a national photon science roadmap, and this has now, in the frame of a big Helmholtz event, also presented to the public. You will find this roadmap if you Google it, because maybe the link is a bit too long to write that down. Now, we have, of course, a lot of conferences here. We were hosting the German Crystallographic meeting, a number of other meetings, and Helmut mentioned already the inauguration of the startup labs in Hamburg, where young people and startup companies have find a home, closely collaborating with us and pushing forward their ideas. And that brings me now to the strategic development of our facilities. You know, we have PETRA III as, let's say, the second best machine, because EBS is now doing always better in emittance than PETRA. In the world, in the high energy regime. I give you here just the amount of users that we have, and I took the values before the pandemic. Oliver will come a bit more on what are the actual numbers. So roughly more than 3,000 users and more than 6,000 user visits per year. And Christian will later tell you a bit about the PETRA IV project. That's our main upgrade project here on site in order to make PETRA an almost diffraction window. The storage ring that will be unsurpassed in performance for quite some time, I would guess. At the same time, we operate flash as a VOV and soft X-ray laser. We also are in the middle of an upgrade. I will come a few minutes later to that back. And our main incentive actually is to do research on structure and dynamic and function of matter at large-scale photon facilities. We look on the fundamentals here, but we also look on instrumentation development and methods development, and somehow contribute also together with you, of course, to solve some of the grand challenges where our analytical tools are required. At PETRA, we have almost all soft or hard, let's say tender to hard X-ray techniques. We can go to extremely small focuses well below 100 nanometers if it comes to spatial resolve studies. And we have a large number of sample environments for in situ and operando experiments. Flash, of course, as you can imagine from the energy range of the machine, it's mainly a VOV and soft X-ray range. It's, of course, dedicated to science at either short time scales, where you can look on non-equilibrium states of matter, transient states. And of course, we have a number of variable pump probe schemes that are available for pump probe experiments. Now, how do all those fit together? We are in 2022 in the beginning. So at PETRA, we are in the middle of the TDR phase. By the middle of the year, we want to provide a funding proposal to the government and to our funding bodies. The TDR will continue with until 2023, and then after the preparation phase, this is the ideal schedule that we have. If everything works and also the funding comes, we could start the shutdown for the upgrade in 2026, and by the end of 2027, hopefully start with the recommissioning of the machine. At Flash 2022, as you can see, we are in the middle of an upgrade. At the moment, the LINAC is upgraded to slightly higher energies with better modules that we have, meanwhile, superconducting accelerator modules. We will have 1 year of operation then after that, and then another year of shutdown, where all the Flash 1 non-tunable fixed gap undulators will be replaced, and also external seeding will be implemented so that we get better beam performance and have 2 independent running undulators that are independent, almost independent of the particle energies of the accelerator. Christian will tell you a bit more, or substantially more, about what's going on at the PETRA IV and how we develop together with many of you the beamline portfolio. Sorry. I also should mention that Lucas Schaper took over the project lead from Enrico Alaria now for the Flash 2020 Plus project, and Helmut mentioned already that Harald Reicher, former science director at ESRF for physical science, is now supporting the PETRA IV project management team and brings in his huge expertise in managing such a project. and especially since he has done a similar task in Grenoble. I also would like to tell you a bit what we do in terms of research. We have it organized now, and maybe you know that already, in 4 research centers. And historically, the first one was a Center for Free Electron Laser Science, where we have with the partners that are indicated here, we do science at ultra-short timescales. But in order to do that, a lot of fundamental things had to be developed in terms of methods and instrumentation, and all of that is done there. Also fast laser development or theory on light-matter interaction. And a science highlight that came from Seefeld, from the group around Henry Chapman. In his group, Eike Meens has fostered a huge collaboration, so I had to cut the authors because otherwise the slide would be full. They have, I think you know that already, or we have mentioned it, they did a very massive screening on possible inhibitors for the main proteases of SARS-CoV-2. And if you can prevent these proteases to work, then the virus might die and cannot replicate anymore. And actually, we identified some hits, quite a number actually, and in the end, one so far has survived all those tests, even in small animal tests, that can dramatically reduce the viral load in the body. So it seems to work, at least in an animal model, and then we have to see how we continue from here. The next center, and as you can see already, the Center for Extra Nanoscience. Also here we have a number of partners, and you see now the building is finished, mostly concentrating, of course, on condensed matter research at the nanoscale, high-resolution X-ray imaging, and EC and operando experiments. The this CXNS center also includes what we call the Nano Lab. I'll come to that later. This is something that's very helpful for you. And also here, a recent research highlight is by the group of Andreas Stierle, that have shown that palladium nanoclusters on graphene are very, very well suited as hydrogen storage systems. And of course, this is a fundamental physics at the moment. But in the end, there was a big resonance outside of DESY and in the world about this experiment. So we are very excited about future development in this field. The Nano Lab actually is something that will support you for your experiments at FLASH and PETRA III. If you need to prepare your sample, we have spectroscopy tools there. We can grow samples. We can do crystallography or X-ray diffraction in order to pre-characterize your samples. We have microscopy and microstructuring facilities there, as well as other microscopes, electron microscopes, scanning or Schell microscopes. So in the end, this is intended to support you in preparation very efficiently the experiments. And as most of you certainly know, if you write a proposal, you can ask for help from the NanoLab already during the proposal submission. The third center here is the Center for Structural Systems Biology. Here in those partners from the northern German areas, and the experts will immediately see that these are all the relevant partners that are dealing with infection research, have joined in order to fight infections. The people work on viruses. I think since we are sitting here due to the virus, I don't have to explain you how important that this research is, but also bacteria and parasites. And with the technology, with cryo and light microscopy that they have in the CSSP, together with our facilities at FLASH, European Expert, and especially at PETRA, we can now cover all the full range that is needed in understanding the molecular processes of infection from the cell and tissue down to the molecules. Here, I would like to show you also a slightly different example. This is from the group of Thomas Malowitz. He is from the University Hospital of Hamburg, but also his group is supported by DESY. And they were looking on the type 7 secretion system. This is a huge protein complex that was solved by cryo-EM that is around the shell of the Mycobacterium tuberculosis. And now we all talk about corona, where we know that corona has now killed something like 5.7 million people in 2 years. Mycobacterium tuberculosis kills about 1.5 million people every year, since years. So at the moment, it's still the most fearful killer in the world. And with this, knowing this structure and this protein that is needed in order to get nutrients in and out to this mycobacterium, one might find ways or weaknesses how to fight tuberculosis. The last center that we are in the process of establishing is the Center for Molecular Water Science. Here we had big resonance by many European and German institutions that want to support. We have started to foster collaboration early science program. we have these 5 pillars here in which research is ongoing. And maybe what is interesting to you, there has been now a white paper published, I think it's available on the internet, that we will want to also use to talk to funding bodies that they can support that by additional funding. Also here, I would like to show you a highlight that's by the group of Gerhard Grübel. And the reason for this highlight is manifold. Of course, it's colloid particles in an aqueous solution, so it's related to water. It's correlation spectroscopy, but it's done at PETRA III in the so-called 40 bunch mode, and the PETRA 4 people mean then the pulses come at a repetition rate of 5 megahertz. Fortunately enough, Heinz Grafsmann and his colleagues, and with a large collaboration, have developed the H-chip detector actually for the European expert, but that can do frame rates in excess of 5 megahertz. So we really can use a single bunch structure to do XPCS on a single exposures and read out each of these exposures, of course, not in CW, but only for a short train of pulses, but we can do that on that time. So these experiments, of course, would dramatically benefit also from a higher coherent source like PETRA 4. And of course, as you can see here, detector development is equally important as the source itself. Now, I come to the user operation. Meanwhile, we are all experts in chromatography because we know how to use these tests. We can hire in biotech labs. We know how to wear masks. And so what were the main issues during last year? Of course, we had implemented some measures to prevent infection chains. We tried to contribute to combat the pandemic, but we also have had, as Helmut mentioned, a few measures installed in order to keep the user operation going, and sample mail-in and remote access were one of the most important issues here. What did we learn so far? Yes, we can, beyond those experiments that we did already mail in before, we can do it in further experiments. This could be an opportunity in future to have more sustainable user operation, because if you have less people traveling, our CO2 footprint will be smaller. However, those users that normally come here and do their experiments, where they just mail the samples, our people have to do the experiments, and that means we need more resources for that. Otherwise, I wear out my people and I cannot take responsibility for that. However, this in part can be mitigated by, let's say, increasing more robotics and automation. But this also needs, of course, the resources for us to get this this whole thing implemented. So in the end, we talk with our funding bodies together with our colleagues from HAP and HATR. And so far, we don't have the funding yet, but the signals are very positive that they understand the case and they are willing to support us. At PETRA III, we could almost fill all beamline slots. People were, and I thank you for reacting flexibly. If people were dropping out due to Corona issues at Flash, it was a bit more difficult, especially since mail-in experiments are difficult at Flash. So, but nevertheless, the people did the best in order to keep the user operation going, and we will hear later, at least from Oliver, something about the PETRA III case. I'm quite proud to say that our safety concept worked so far. No infection chains have been started at the facility. However, we are very lucky because the experiment shut down in 22nd of December before Omicron arrived. So whether we could keep this success under the present condition, I'm not absolutely sure. We have, Helmut indicated that if we go to more robotics and automation, we need, of course, the necessary tools, but we need also a standardization of the experiments to a certain extent, at least to those experiments where it's possible. And here, that's something we need your input, and that's probably also something we have to discuss on a European level within the LEAPS framework. And here, I especially would like to thank, of course, my staff that has enabled keeping the machines running under these difficult conditions, but also you, the user community, for understanding and supporting our safety measures. Now I come to an important part, new criteria for proposal access and new access schemes. So far, all our proposals have been ranked only to the scientific excellence. We never looked what is the socioeconomic impact of this, or is there any application behind that? And very often, like, let me give you an example. Someone looks on a new material, he investigates the properties with the synchrotron, and he gets a high ranked publication. But then comes the aftermath. How do I get that in an application? How can I really make it useful to the society? For such experiments, you hardly will get beamtime, because the main thing is already done, the exciting one. And we want to make socioeconomic impact on application a second criteria. And what could be possible criteria in order to judge that? The proposal should following, I mean, it doesn't It's not enough to say, oh, it has high social and economic impact. You have to show, present a robust or credible exploitation plan, or it's a work that you prepare in preparation for operating a startup company, or also you are in the development of a project, as I mentioned before, and you are with the experiment, you can increase the technical readiness level. So we will install also flexibly, and we have to learn that now with our PRP, additional expertise in order to judge this. And we might need to get external experts to that, but we will try to do it as fair as possible. And we hope that now also those proposals that have a high social economic impact have a chance to get beamtime. We have already now a number of different proposals. We have regular proposals, long-term proposals, block allocation groups, rapid access, CRT type proposals by those institutions that finance entire beamlines. We have Flash as an additional the NFFA proposals, and of course industry access. So, but so far they are all individual proposals, and we have not really strategically steering that, or just putting, let's say, an emphasis in turning for strategic directions. So this is one thing. So we want to really have a more strategic approach for the user access, but also people tell us, listen, we have a larger research program. It's not instrumentation, but it's research, but we need more than one beam time, and we need also more than one beamline. In order to accommodate these needs and also these strategic aims, we will introduce a new access scheme. We call them topic bags that are impact driven with some conditions. And as the first one together or in parallel with European expert, we will have a call for a topic bag in water research. And that's in conjunction with our Center for Molecular Water Science. And if you are interested in that, then please note down in the 2nd and 4th March, we will have the water days, and within that you probably have opportunities to foster collaborations in order to go for such a topic. In future, we could think about additional impact-driven topics, but these are still under discussion and we have to work out the details. Access of industry is of course also possible here. So we have, of course, the people that directly pay for the income, industrial companies, or they do it through service providers. These are small companies that just do the job at the synchrotron. For the larger ones, and that's actually quite efficient, and in structured biology, it's a role model. Of course, industrial companies very often also collaborate with us if new techniques or things need to be developed. Or, and I think this is also a very valid way, very often industrial companies discuss, collaborate with university institutes and go through the normal proposal round, publish their results, but there's also a way how industry can access our facilities. Now I have to come to a difficult issue. Data, you know that this is the rise of the data alone of PETRA, when you have to add Flash, and if you add European expert, it looks even worse. So far, we migrated after 180 days after you last accessed your data. So half a year after you accessed your data, we migrated it to Dcache. So we never delete data, but we put them to a slower cache, a slower disk system. The GBFS, just by information, is a very fast disk and very expensive also. So we migrate them, and then they will automatically copy to tape. From the mid of February on, so from the next beam time start on, we will move the data to the Dcache 180 degrees after the beam time. So we keep it half a year on a fast system, but then it goes on a slower one or on tape. If you need it, you can get anytime the data back, but you simply have to free up the space here because that's expensive and it's very scarce. Also on the long term, we will implement a data policy. I think we indicated that once, to the rules worked out at within the Pandata collaboration, and that will be similar to ASRF or to PSI in order to accommodate the FAIR principle. And I think for EU proposals, you actually need this open data policy. Now, be sure we do everything in order to meet your needs, and your data are secure here. We always have 2 copies of your data, either on disk and tape, or even if it's copied to tape here, they are twice on tape. But now I have a request to you. We have experiments that fill up all our space in one day with extremely high data rates. If we want to support you in doing every crazy experiments here, if it has a scientific case behind it, but please let us know before if you have such an experiments, because that needs to be set up. We need to to loan disk space maybe from somewhere else, from other units in DESY. We will try everything to make it work, but we need to know it in advance. And if you fill up our disks, our entire disk space in 2 days, then all the other experiments will have to stop working operational. That's not what we want. So please contact the beamline manager and IT experts way before you start your experiment. And one way, of course, to reduce the data rate is what Anton Bartin and his scientific computing group is doing now. They have some success rates now already, but after working on more than a year now. For example, they were able on the fly at 133 hertz to process the data of a 16 megapixel Eiger detector, which is quite so compute intensive, but things like this work. And this is, of course, a way to select data, to sort out data, or even to process data and reduce them significantly. Also, XPCS has been speeded up by up to a factor of 60 in the computing. There are many themes that the people work among, and the most importantly, of course, to provide near-time and real-time analysis that you can feed back to your experiment. This is especially important for in vitro and in situ and operandi experiments. And of course, we're doing this in collaboration with universities, within Daphne, I mentioned that already, but also within European collaborations and within leagues. I mentioned the two right columns here, but I want to dwell briefly on our graduate school. We have set up a data science graduate school. Here is that the graduate students have always two supervisors, one from the domain, let's say from biology, from physics, chemistry, but the other one from either applied mathematics or informatics. So here we try to educate experts in data science in the future. And I think late in the year, there will be another call for PhD students. And if you are interested, either you Google Dash, it is easy to find, or you contact Nina Roringer, who is in charge of this activity. Now let me come to towards the end to a few scientific highlights. Since this is the normal users meeting, or Flash users meeting was yesterday, and you might not have been there, I want to give you a glimpse what can be done with Flash. And here was the question that people want to answer is, how fast actually can we make a magnet switch? And this is an ferromagnetic phase transition at 360K. And they use if you know the band structure, this is quite distinct. You can, by this Hextov electron spectrometer, we can measure that directly. And the people found out by pump probe experiments that it takes about 350 femtoseconds until the new band structure is established. Of course, the lattice and the spins might take a bit longer to adopt the new band structure. And but this is not really known so far. But at the moment, it's expected that after roughly a picosecond, the phase transition has been taken place. So this is, you bring in energy via a laser, and then you do this, and then you probe the whole thing by looking on the band structure. And you can do that at the time resolutions in the 100 femtosecond ratio. We have three larger user consortium at the European X-FEL. One of them is the SFX consortium led by Henry Chapman and the CFREL group. And here, and I think Helmut told you already, maybe you did not notice this experiment. So what they did, they used microcrystals in this flow device where you can mix in, let's say, inhibitors or other things. And what was important here is just to look on this lactamase. This is also an enzyme in Mycobacterium tuberculosis, which is actually developing resistance, and is very important because it attacks the antibiotics. And what people showed here, that you get with this method extremely good data, and you need very small crystals in order to get some short diffusion lengths. And this is more now not exploiting the high time resolution of the X-ray, but the high single pulse intensity, because from one shot you get already the diffraction image, and by collecting thousands of them, you get very good electron densities that allow you even those studies. So we look forward for new results in that field. Oops. Now it goes. Then we have the HRIX consortium. This is the Heisenberg-RIX consortium. It's a user consortium targeting for soft X-ray spectroscopy, inelastic spectroscopy. The experiment, despite the pandemic, was commissioned last year. It fulfills more or less all expectations. They have done first test experiments, as you can see here. And now I don't go through all the details, but now we are looking forward when they really can start to harvest science with this instrument, which is actually at the soft X-ray SCS instrument at the European X-ray. And last but not least, the HYPER consortium, which is led actually by HFDR with major contribution also from the UK. And here, Peter Liermann and his colleagues, they used the piezo-driven tech, which diamond angle cell that can produce a lot of quite high strain gradients. And with that, they were able to directly observe metastable I7, which is supercompressed water. And this experiment has now become possible at this new stage with these high single pulse intensities in the hard X-ray regime at the European X-FEL and the corresponding technology. That brings me to the more or less last slide. What is the outlook for next years? And maybe you noticed that we have had to move the SRI from August last year to spring in the hope that there will be no COVID. The hope was, of course, bad and did not work out. So at the moment, it will be a fully online event, and the registration is open until February 1st. I also would like to, especially as a young colleague among you, I would like to point out the diffraction limit light source, limited synchrotron light source, and next generation free electron laser Pareo seminar. I think there are still open slots. It will be a hybrid event, so in part people can go there, and others will be connected via online tools. And here also the registration is open until the 1st of February. So young guys, please, or young people, please register. That you have put together a very interesting program from the basics of the sources to the experiments. And at least when I asked last time, there were still 3 slots available. Next year, we also have the science at FEL. We will have the molecular water day, Center for Molecular Water Science, the water days, where you can find friends and colleagues to go for, let's say, joint proposals in the water call. And of course, there will be many more events. Stay tuned on our webpage. There will be certainly, at least online, many things ongoing. That brings me to the end of my talk. In the summary, despite the pandemic, actually, we are still able to pursue a quite vivid research program, methods development, but also trying to really solve some problems. We operate our facilities as good as it's possible, also to your help. We have an upgrade program running for FLASH, the seeded high repetition rate FEL, and for PETRA IV in the middle of the TDR, producing close to diffraction limited beams in the future. I would here take the opportunity to thank, of course, my entire staff for keeping the lab safely running under these conditions. That was not easy, and a lot of individual efforts has gone into that. I would like to thank you, because without you and your discipline in obeying our rules, we would not have been able to maintain user operation running during these very difficult times, and also for the continuous support of our collaborators in operating the facilities, namely Herian and EMBL. I also would like to thank the DESY Review Advisory and funding bodies. Without that, of course, would not be possible. And last but not least, the organizers of this user meeting, because even if it's online, it's quite a lot of work for those people to do. And last but not least, I would like to point out to you, this is our new highlight brochure. I think it's available on the web. And if you want to learn more what's going on in science or in instrumentation development, this is the right source to go. And for you, I can just say thank you for your attention.
Thank you, Edgar.
And I'm, of course, happy to take questions.
Yes, thank you, Edgar, for this great overview of photon science here at DESY. Are there any questions? Melanie, did you see anything in between?
No, I just forwarded some information, so there's nothing in the Q&A, but you can also raise your electronic hand. So now I see a question from Jan de Groenewald that I will click on answer live. So maybe, Jan de Groenewald, maybe you want to just raise it directly. You can raise your hand and we can hopefully give you the rights to speak. Matthias, can you do that? I'm not sure how to do that. I still need to practice here. Allow to talk. Okay, I found it. You should be allowed to unmute now.
Yes, now you can hear me.
Yeah, I hear you, Jan-Dirk, yes.
Yeah, hello. Yeah, thank you very much, Edgar. Really nice activities, nice centers, and so on and so on. Also the highlights I liked very much. I was asking myself, I mean, you have lots of activities with respect to ERUM Pro and Verbundforschung. So I assume some of the highlights are also related to this, and you benefit a lot from that. But maybe you can give here also some comment on that. because you know the
Oliver
Verbundforschung
does it in his talk, of course.
Yes.
One of our central activities here is the close collaboration with the user community, and the ERON Pro financed, or in former called Verbundforschung, financing to university groups to assist or contribute to method instrumentation development is crucial for our success here. And I maybe Oliver in his talk dwells on that a bit more, but it's extremely important. And I can tell you, we are overwhelmed by the number of 99 proposals to DESY facilities in the last ERON Pro call. So that shows the large interest also of the user community in this type of collaboration.
Yeah, thank you.
Any further questions? Probably not. I also don't see anything in the question and answer function. So thank you, Edgar, very much. And we will move on to the next speaker, Oliver Seeg, who is the coordinator of PETRA III, responsible for diffraction and scattering experiments. And yeah, he will give us an overview of PETRA III, the user operation and projects. So please, Oliver, go ahead.
Yeah, thank you, Sadia. And in fact, I'm not the only one coordinating PETRA. It's also Hans-Christian Wille and Christian Schröer. And I'm, of course, here talking on behalf of them and also on behalf of the PETRA teams, of course. Yeah, and anyway, I will show some facts on user operation projects of the last year with some outlooks, of course. So Edgar has shown already some facts of PETRA, and here I want to mention that the PETRA extension project, which you may know about if you are like regular user here, is now finalized, meaning that all the beamlines which we have planned for the PETRA extension are now complete and in user operation. So in regular years, we would have a party. Of course, that's not so easy in our years, but this is like a big success that we, though the Corona crisis was kind of not very helpful here, we could finalize the projects. So now we have 25 beamlines online, and there are only a few slots free still. And so we want to fill these slots still in the running period of PETRA III. So there are 2.5 beamlines to be filled. Edgar was already mentioning that we can deliver X-rays with high photon energies, but also we have a soft X-ray beamline. But since recently, we have online a bending magnet beamline, which can also offer beams in the VUV and UV area. So, and the condition that we run PETRA III at 6 GeV, this enables us actually the high photon energies here, the 200 keV we can reach at beamline 61, the large volume press, and the wide beam diffraction beamline. So you know that at PETRA III, the emittance is excellent for a third generation synchrotron radiation source. In particular, in the vertical, we reached the 20 picometer radian, so the source is very small, just a few microns high, and also the divergence is just a few microradian wide. And in the horizontal, we reached today 1.3 nanometer radian, and the next talk will be about PETRA IV, where we want to squeeze down this number to numbers roughly similar to the vertical emittance. So this we hope that we can in 2028 offer you then beams for the ultimate 3D microscope. So for you as a user, of course, it's important to know that we usually want to offer 5,000 hours for the users, and that we have two modes, the timing mode and the continuous mode. And for you also important to know is that the emittance parameters of these both modes, they are not really different. So that means if you are not interested in any of the modes, you can just come to DESY at any of these times and can measure. So we have this 25 beamlines operational, and they are distributed over 3 halls. So, you know, PETRA is like very large. It has like 2.3 kilometers circumference. So we cannot cover the whole ring with the experimental hall. So they're like, we have these 3 halls in the north, in the east, and in the northeast. They're called Peter, Paul, Ewald, Max van Laue, and Ada Jonat. And we, of course, offer all the methods which are usually available at synchrotron radiation sources, and have, of course, at the experiments, optimized setups which make use of either the beam parameters or make use of like dedicated sample environments. So like, especially, of course, at PETRA, we are making use of large coherence volume, which enables also a small focus. But of course, we have beamlines with high flux and experiments with in situ and operando methods available. And as Edgar was also mentioning, and I also do it here, is that we would not be able to run our beamlines without our partners and friends from the various institutions. So importantly here is like EMBL running the bio beamlines P12, 13, and 14. Then Hereon, formerly HZG, operates like beamlines and end stations, mostly on material science. We have the big cooperations with India and Sweden, which enables us to build new beamlines, to build experimental setups, to buy detectors, and to also to hire persons. So we are very grateful that this is like this, both corporations are extremely fruitful and lively. We have several involvements of Max Planck and Helmholtz, and new are actually the Saxony DESY Corporation and the KIT DESY Corporation. And I will elaborate on this maybe next year, because this is just newly, freshly started, and so that I don't give the details here. So at PETRA III, the beam lines are usually very long, so like from 60 to 100 meters long. And this enables us to put in more than one experiment at each beamline. So obviously at 25 beamlines with more than 50 experiments, it means that in average we have 2 experiments per beamline. And most of them are kind of dedicated to diffraction and scattering methods. And here I want to point you already to the new beamlines, which are on the horizon in the next years. This is beamline P25 and 63. The last 2 beamlines to be filled, and the beamline P25 and 63 I will show later, like a few outlooks on this, so I'm not going into the details here. But if you like to get, of course, all the information on the beamlines, you can visit this homepage here, and there are links to the single beamlines. Yeah, and here you see also there's still one end station which we built in cooperation with the KIT from Karlsruhe. So for you as user, of course, it's interesting to know about the beamtime schedule. This is the planned schedule for 2022. I said in the beginning that we try to reach the 5,000 hours, but this depends a bit on the work and which has to be done at the machine, and also in the infrastructure which is surrounding PETRA. And in fact, in the summer, we have to repair a big chiller which runs for PETRA machine. And so we are not able to reach this 5,000 hours exactly, but it's very close, right? And as you see also, this year we start user run already mid-February. This is different than all the other years where we had still to do upgrades on the machine to accommodate the extension beamlines. But as I said, this work is done. And so we hope that we can offer the early beams also in the future. So let's say starting in February. And you should have in mind the call for proposals. So if you want to apply for beam time, there is the March call. This call is open right now. And then there is the September call. And you can, of course, go at DESY.de and apply for beam time. And as Edgar mentioned, in the September, we will have open this topical call, and there will be mails for you to announce this separately. But this topical call is for the September call. I want to mention the availability statistics on PETRA of the last year. So last year we delivered 4,500 hours. So basically meaning that we reached an availability of 97.3%. This is unfortunately not exactly the 98% which we usually want to offer, but you should have in mind, I showed it on the first transparency, that parts of the beam of the synchrotron itself, of the storage ring, are from the 70s, right? So they are like pretty old actually, and so once in a while things fail. But there are also external reasons for some of the failures. So I have listed here the most prominent ones. And especially in the summer, we had several power glitches from external sources. And we have set up now like a working group and find a way if maybe in the midterm or long term we can like compensate power glitches from the outside. And this is actually already would have like a big impact on the availability and especially on the mean time between failure. Still, we are not too bad. And I want to thank here at this moment our colleagues from the machine department that they keep PETRA running for the users and for us. So if you look into the user basis, you see that we have in last year, we had like almost 3,000 unique users and 6,400 visits. And if you compare this to 2019, you see that we are almost back to the numbers we had in the pre-corona times. You remember maybe in 2020, these numbers of user visits and unique users were pretty much dropping down. But now we are almost back. Though one should also, of course, have in mind that now we have 3 beamlines more running, yeah. But it means that first of all, we were like successful in offering the beam time, and you also were, of course, like trusting us that we can operate PETRA in the Corona conditions. And I thank you here already, like Edgar did, for your trust and your dedication that you applied for beam time. And we're as flexible as Edgar said by like pushing the beam times forth and back. So this is like, of course, very valuable, your dedication here. So if you look, we are also back with a share of roughly half of German users. So, you know, last year, the amount of German users was roughly 70%. Now we are back here. And again, as in the previous years, pre-Corona, most of the users come from Sweden, France, and India. But as you see, we have also users from overseas. And if you look into the statistics of on-site, remote, and mail-in and data-only access, you see that this is what Edgar was already mentioning, something which is and a development which will go in the future or in the direction of more remote and mail-in access. So obviously for the Germans, it's easier to travel to DESY, yeah? But already for the European facilities, they prefer kind of remote access. And this is of course more true even for the overseas. And as Edgar said, we are of course like offering remote and mail-in services, because this is something which is like very effective and also something which is required and requested by the users. But we need, especially for the mail-in, more personnel, and we hope that we will be supplied with the funding to enable you this kind of service also in the future, even like in the more way. In fact, like I would say, like at least half of the beamlines are offering these services in a regular. So if you go into the publication statistics, that's like a very nice observation that again in 2021 we have more publications than 2020. And I should also say this is a preliminary number. Usually over the year, this number is increasing by some more tens of beamlines. So publications, so we may even reach the 800 publications. And very interestingly, or very like prominently here, the impact factor, the average impact factor is at 7.6. And of course, this is your work and your excellent science, which is like reflected in these numbers. And I again thank you to do this excellent science at our beamlines. And I have like I beg you, please don't forget to register your publication also at DESY. This is very important for us because we have to justify our work in front of our funding agencies. I want now to present some finalized beamlines, which we have finalized actually last year with the first users. And there's like the beamline P61A, or like it's the end station of the beamline P61. It's the white beamline for material engineering science. And they are using the white beam for energy dispersive diffraction, but also for radiography in material science. So it's in the North Hall, obviously. This magnifier also points to where the beamline is. So the hutch itself is like has like a lot of space for different setups, and especially on the heavy load diffractometer, you can put in like heavy equipment like this in situ laser welding experiment, which you see here. And the white beam is especially also nice to use to get like a very fast data on stress, surface depth depending stress, depth depending stress. So basically it's called the Laplace space depth. So at the different photon energies, the penetration depth is different. And so you can with one shot basically analyze the stress. So that's now running, and the further developments I want to mention here, the new radiography detector, which should be able to run at 100 kilohertz, and this would be then the speed at which you can get images on this. And you can then, of course, measure operando and in situ experiments here. Then we have the ASAX beamline, which opened the doors for users in October. And this is the SAX beamline, but can easily change the photon energy during the measurement. And this is then, of course, used to be sensitive to elements or metals, whatever, which have like absorption edges in the range of energy scanning. Yeah, this is called then ASAX, so anomalous SAX. And here are already some very nice data and excellent data from the synthesis of nanoparticles from zinc oxide, which are doped with erbium or ytterbium. And they scan the energy from 8 to 10 keV, and there are like plenty of absorption edges actually in here. And this you do in the SAX and in the wide angle scattering. And so you can, when you analyze the data, very easily distinguish the scattering contents of like the different contents. Then I want to mention our superlumi beamline P66 that's sitting here on top of the PETRA ring. And this is our time-resolved luminescent spectroscopy beamline with UV and VOV light. They got the first users in September. And I want here to mention already the first scientific highlight, I would say. It's like submitted, but I got the permission from Alexei Kotlov, who's the beamline manager, to show the data. This is like, and these guys, they were measuring actually in October, so they are very quick in actually writing up their results. So this is like an example from medicine or like medical applications, I would say, because it's about the success of disinfection of like a surface. So like if you are in the hospital or so, you know that bacteria are like kind of detached, attached to the surface, and you want to disinfect these surfaces. And that's for like the standard form of bacteria, like easy, they're like ethanol or other disinfection material which can remove them. But bacteria tend to modify their shape into the shape of spores, and these spores are very tough and not easy to remove. And now the question is, if I like apply a disinfection on these surfaces, is there any like probe or any like way of figuring out if I successfully remove the spores? And in fact, as of today, there is no like easy way of figuring out if spores also have been degraded by the disinfection. So the idea is here to use the emission spectrum of the spores. Like, so what you do is you excite, you illuminate them with pulsed UV light, and you measure the emission spectrum first in time, but also integrated. And the people here, they did this for viable and for dead spores and saw that there is actually a significant difference in the emission, which would give you, or which gives you now the opportunity to develop an instrumentation to measure the success of disinfection also in terms of the spores. So these beamlines I showed you, they have now the users, and I want to present you like a few future and ongoing developments. First of all, there is a beamline P23. There was some space behind the experimental hatch 1, which is like a diffraction hatch. And in cooperation with KIT, we are building here an end station for imaging. So the hatch, the experimental hatch, is already finalized. We are now changing the beam pipes and the interlock. And what has to be built, hopefully in summer or fall this year, is the preparation hatch and the control hatch. And hopefully end of this year or beginning next year, we will have beam on in the experimental hatch. And in here is the imager HICA. It's called HICA. It's kind of originated from ANCA, the synchrotron radiation source in KIT, and it has been transported here. And this is then like an instrument which can like work on hierarchical imaging in material science, but also on with biology applications. So this is actually all on track, and we hope that, as I said, we can have the first beams at least beginning of next year. Then we are building the beamline P25. This will be a beamline for biomedical imaging powder diffraction, and it's the innovation beamline. We hired a beamline manager. She's Catherine Spears, and the beamline is built in cooperation with Gerald Faltenberg and Martin Etter from these According beamlines. And this beamline will host like a fully automized powder diffraction instrument and also a fully automized imaging station. And we hope, so the design is more or less complete. So let's say we have still to do some small adjustments, but maybe we can actually get in 1.5 years the first beam in here. And there is also included a hatch for wide beam experiments. Or let's say pink beam experiments. Okay, so then there is like the last slot to be filled is in the North Hall P63, and here we have a cooperation with partners from Max Planck. It's like Beatrice Roldan and Serena De Beer, and with them and P64 and 5, we will set up a third beamline for absorption spectroscopy. But here in this new beamline, we will also have the option or the opportunity to include ZACs and powder diffraction into the scheme of experiments. So enabling us for like operando studies of batteries, catalysts, and maybe also including pump probe. So this is like beamline is in the design phase, and still some like funding things have to be sorted out. But we are very sure that we will be able to deliver beam before the actual shutdown of PETRA III. So maybe first beam is foreseen in early 2024. Now, in the last two slides, I just want to give you like a few science examples. So I'm not covering, of course, the science examples which will be presented in the next few hours. I'm also not looking at this, what Edgar has shown. So there are like some others, and this is like an example from University of Tübingen, and they have done an experiment on egg white. So this is like a problem which maybe everybody of you knows from your own kitchen. So if you try to cook the egg on the point, that's not so easy, and sometimes they are too hard, sometimes they are too soft, and basically you need to understand what's actually going on a molecular level when cooking the egg. So what they did is they took part of the egg white and heated it up, and this is basically the time scale you see here, and then they illuminated this at P10, that's here, with coherent beams. And if you do this, you are getting like a speckle pattern, which is kind of a non-static pattern if the molecules move. And so this is called XPCS, X-ray photon correlation spectroscopy, and you are studying the process of gelation and the cross-linking. So this is like the correlation map, how it's usually displayed. And if you start here at 0, and in the liquid phase, there's basically no correlation visible. And now if you wait longer, you see that the correlation pops up, basically longer time scales pop up. That's exponential growth of the aggregate, means like aggregation. And this goes further and further with the slowing down of the dynamics that basically would say the egg is cooked, okay? So, but then it turns out if you cook a little longer, actually the temperature was 80 degrees, so it's not actually cooked. So if you wait a little longer, you see that the dynamics becomes faster, like in a periodic fashion again, and then slows down again. So this is like a strongly heterogeneous behavior, and you can actually do this at different length scales and figure out that at small length scales, so small length scales are here, this is Q. At small length scales, the heterogeneity is larger than at long length scales. And this means that the egg white is something which is called attractive colloidal fractal gel. And this is maybe the reason why the egg is not so easily cooked. So this is basically this science example. And I want to show you another science example. This is a Nature paper which is related to industrial research. And this is also, important to know that nice and good science can also be linked to industry applications. So this is about the formation of zinc oxide species for the efficient propane dehydrogenation, and has been done at B9P65 in the north. So they have basically used EXAFS and XAFS methods. So the idea of this is that you need like an alternative way to generate propene. Propene is actually propylene, it's the same substance, right? And this propene is a chemical which is the raw material for several other materials like acetone. So for example, if you buy acetone, it has very likely been produced by an oxidation process of propene. So today, there are a huge number of plants, and they are really large. So here's a new dehydrogenation plant. It's like large facilities, and as of today, they use platinum and chromium-6 as catalysts. And this is first of all expensive because of the platinum, but this chromium-6 is also like an evil stuff, right? This is, you want to avoid this because it's kind of like very oxidizing, poisonous, and so on. And basically you want to replace this with something environmentally friendly silicon oxide, silicate catalysts. And it's known that you can actually do this propane to propene transformation. But now the question is, what's actually going on at the catalysts on the surface? And here they have these people here. They used XAFS and EXAFS to very detailed analyze the actual reaction, of course, using also complementing tools. And they were able to to get the structure and the actual chemical reactions on the different steps from the propane to the propene. And this is like very important information, because now you can design basically your perfect zinc oxide catalyst. So that's it. Thank you very much for your attention. And also I want to thank, of course, the PETRA team to supply the beam time during this difficult times. And also I thank you for them for their flexibility and yeah, that they stand our needs. Yeah, that's it. Thanks.
Thank you, Oliver, for this great overview of what's happening at PETRA III. Are there any questions or comments to Oliver? So please, again, as a reminder, put your questions or comments into the Q&A function.
So there is some, like in the question and answer, there are 2 questions. Do you want to read them?
So,
yeah, there's one from an anonymous attendee, which actually refers to Edgar's talk, but we can go to that later. And then Andreas Stierle made a comment, but I guess it was for one of the examples that you were raising, which refers to the hydrogen palladium cluster study. But this is more a comment and not
more a comment, yeah.
So
for the anonymous attendee, I can also mention here something, right? I guess it's related to the additional call on the topical call, right? Which is or is this? I think so, maybe. I don't know. But this topical call can, of course, also contain the fundamental research, right? I mean, in the topical calls, we think of having groups of persons, of science groups who are working on a topic on the topical call. Like if it's water, for example, it could be something like water splitting, or could be like high pressure experiments. It could also be, and that's what we think is also valuable for you as users, it could be that you combine the forces, right? So there is like somebody working on very basic fundamental questions on whatever water splitting or so, and other persons think, okay, this is something which we want also to do on the application level, and maybe something where you say, okay, I need high pressures for this. I mean, this is now artificial, but could be. So, and then you would go for different beamlines for this, and would be usually independent, and maybe you fall below the level of what you get actually at beam time. But here it's like a way for you to get what in German is a Verbund, like a kind of friendship of people, yeah. So like the friendship of the ring, more or less, and you basically apply for this beam times, and can, if you like, also apply at different beamlines, and then will be supplied with beam times over 2 years.
Maybe I can just comment on that as well, just to give you a bit of numbers. At the moment, 95% of our proposals are these individual regular proposals of the beam time. 5% or 4% is going via other channels, except the CRG times, of course, because that's not public beam time, then because it's paid beam time by the funding agencies or for the funding organizations. Of course, we would like to get this strategic access or target access at a higher level, but we still, as Oliver says, first of all, it doesn't exclude fundamental science. And I guess a largest fraction of the beamline still will be in the individual proposals. But having this targeted access will, I think, enable you and also us really to target pressing questions of our society in a more efficient way. And this is the rationale behind that. And of course, we also need probably still doing basic research and understand these processes.
So there's another question in the Q&A by Reshev Tenne from Weizmann Institute, and it goes directly to Oliver's talk. So the question is, can you comment a bit further on the new imaging option in P23? What would be the spatial resolution of this beam?
So at P23, you will be able to do, you will be able, I mean, they will host several experiments like on this large granite. And in the nano focus regime, they would obviously offer also nanometer resolution. I cannot give you now the exact number, I should admit. I mean, for users, I would say this is open in 2023, so definitely next year we will have some information on this. But if you want to, you can also contact the beamline P23 and they will give you the detail. But they have they are also going for like a flat beam options, like a large flat beam option, and they are going for the nanofocus option, and there will be also the possibility to do tomography on a surface, so that's luminography. So the exact number I cannot tell you, but it will be below one micrometer, definitely.
Any further questions? So if that is not the case, and also considering the time, I would like to thank all the speakers of this first morning session, and we will meet in 15 minutes back after the coffee break. Thank you very much. Goodbye.
Good morning.
Hi.
Hallo, hallo. HC wird die Sitzung leiten und ich mache im Hintergrund die Fragen.
Okay. Yeah, good morning, everybody. And welcome back to the second session of the users meeting today. My name is Hans-Christian Wille from PETRA III, and we're going to start right away with our first speaker, who's Christian Schröer, who is a certificate of PETRA III and coordinator of PETRA IV project. And he's going to give us an overview on the PETRA IV upgrade project, the status of technical design and the beamline portfolio. So please, Christian, go ahead.
Thank you very much, Hans-Christian. Good morning, everyone. I'm very happy to give you an upgrade of the technical design and the beamline portfolio this morning. This is, of course, on behalf of my colleague Riccardo Bartolini, who is the project manager from the machine side, and the entire project team that have been doing some really exciting work over the last year, on which I want to report. And of course, while there are many things ongoing, two things stand out, and I'm going to focus basically on the technical design of a new lattice and on the beamline portfolio that has been developed last year. Now, to bring everybody up to speed, PETRA IV is the big upgrade project of our synchrotron radiation source at DESY. And PETRA IV will be an ultra-low emittance source, which is the ideal microscope for chemical, biological, and physical processes, being able to look and span all important length scales from the atomic level to the macroscopic world, and by that uncover the structure of complex systems. In that, it is, as Helmut already mentioned, making a substantial contribution to basically a sustainable future, because it allows us, of course, first of all, in terms make advances in health, but also all material science questions which are related to energy and other important grand challenges are involved in this. And of course, PETRA will contribute to all these grand challenges and to all the fields of science, both in academia and in industry. So if you are interested in more details, of course, this is already a little bit older now, you can have a look at our conceptual design report, which is available also as a paper copy if you contact our project office. But there you find, of course, the main science case for this new machine and a lot of details concerning the technical implementation. Things have changed quite a bit, and this is also part of the topic that I have today. So what makes the difference for PETRA III to PETRA IV? And so the main point is that the electrons in the storage ring can be focused much better in phase space, meaning that their divergence and the size of the electron bunches can be much smaller than at PETRA III. So if you compare this to a single electron emits into a certain cone, and corresponding to this cone there is a certain effective source size that is basically the diffraction limited source size that comes with this divergence. And so you can think all the electrons, they radiate in all directions. And in this bunch, well, of course, at current emittances, this is pretty much in forward direction already, but the cartoon here is still pretty valid. At PETRA IV, this will change in the sense that the electrons will be focused much more to a similar point, and also their divergence will be very small, so that they effectively irradiate into a much smaller cone that corresponds already pretty much to what a single electron emission is about. And that makes the source nearly diffraction limited. And this is, of course, very interesting because you can then losslessly focus this beam and basically do microscopy with it. And what it means, if you're at the diffraction limit, is that you get optimal spatial resolution in real space and in reciprocal space at the same time. And this shows you that you can actually really cover in one experiment all the length scales simultaneously from the atomic to the macroscopic level. And this is what I was referring to. And of course, if you want to study chemical, biological, physical processes, this is an ideal tool to do that. Now, what do we need to do in order to get to that point? Of course, at the heart of it is the accelerator, and in particular the storage ring, which has a new baseline design. And this is what I'm going to focus on a little bit. The so-called hybrid 6-band Acomat with damping undulators is now our latest design, and it is going to be the design for this new machine. And besides the machine itself, of course, we need to then upgrade our beamlines to make best use of this fantastic source. And for that purpose, the beamlines will have to be changed, and we will need more space. And in addition, this means that in addition to the existing 3 experimental halls, we will need another experimental hall in the west that is going to be added also within the project. And of course, we want to be as sustainable as possible, keeping the infrastructure as much as possible that we already have. Now, concerning the timeline, this was already shown by Edgar. Now I zoom into the PETRA project. As already mentioned, we are in the technical design phase and getting ready to submit a funding proposal for the full project, for the basically for the implementation phase. And of course, for that, we also work towards a detailed technical design that will enable then, of course, to do all the rest. Now, today, I want to focus on these two this year's highlights, namely, first of all, that we now have a significantly improved storage ring design. This has really great implications, and I would like to thank our machine group very much for all this work. This is really something that you will see as a user, you will profit very, very much from. In parallel to that, but of course, based on this new design, we will develop, or I have developed, a beamline portfolio, and I'm going to show you the current state of it as we are of today. So diving right in, let's have a look at ultra low emittance storage rings. And so basically, since the beginning of last year, we have a there came across a new idea for a new baseline lattice, namely this so-called hybrid 6-band achromat. And so just to, here I would want to state the main advantages, in particular also to all the users. So this is still under scrutinization, but and the exact parameters are still under study, but we are soon going to have lattice freeze by the end of next month, and then be able to move forward in the more detailed design. So basically, I'm going to explain this in a minute, what actually this 6-band achromat and damping undulators are. The main advantages are that we get a significantly increased lifetime and stability, and this is, of course, for the user operation extremely important. There is simplified injection, and this is also something that cannot be underestimated. Rather than having to swap out individual bunches and put full bunches back in, accumulation as we do today will still be possible, and with that, of course, all operations become much easier. One really great asset of this new lattice is that we will be able to have 9 cells per arc, meaning that we can preserve the overall structure in the Max von Laue Hall, and of course reuse most of the existing infrastructure, which is extremely helpful, but it also gives you additional beamlines, which were in the previous design that was presented a year ago, was not possible. So there will be better performance in timing modes. So all our timing colleagues will be able to run the similar modes as at PETRA III. The whole thing comes at a price. Due to this, accommodating 9 arcs, the straight sections have become a little shorter, and also the overall emittance is slightly bigger than in this previous so-called combi lattice that we presented, and so there is a slight decrease in brightness. But I guess we're still way above everything else compared all over the world. So I guess we're doing quite. This is something that we can live with. In particular, as we get additional beamlines, namely 1, 2, 3, 3 additional beamlines compared to the old the other scheme. So now, what is this hybrid 6-band achromat? So at the beginning of 2021, there was there was put forward a really transformative idea to improve the storage ring, and this came when Pantaleo Raimondi, former director from ESRF, visited DESY to work on this. The lattice dynamics. And so the idea was to move from a 7-band achromat to a 6-band achromat and make extensive use of so-called damping wigglers to deliver these 20 picometer emittance that we were targeting at. And I will show you how this comes about in just a minute, but just to show you actually what this new lattice looks like. This is a typical diagram that accelerator physicists tend to show. So down here you have a schematic of one cell. Basically one cell is 1 unit of electron beam optics between 2 insertion devices. So these are the two ID sections here. And in between, of course, you need to take the beam around the curve and refocus it properly to create the same conditions of the electron bunches in the next cell that you had in this previous ID section. And so now this is based on 6 bands done partly in permanent magnetic technology. And these are fancy magnets in the sense that they are that they have gradients both longitudinally and transversely, and this is basically the key of this new design. Of course, in all the sections where there are no beamlines, there will still be insertion devices, these so-called damping wigglers, and they will damp down the emittance further to our target value of 20 picometer radiant. But before we get to that, perhaps I need to explain a few of these technical terms. So first of all, the hybrid 6-band achromat. So what does this mean in this context? From optics, it is clear that you want to be able to image different colors, meaning different energies of photons from, for example, from one point to a point. And here, this is very similar. The electrons in the storage ring do not all have the same energy. This is slightly varying. And of course, you want to transport the electron bunch from one ID section to the next one without this bunch falling apart. And this is why you need to refocus it in all phase space dimensions. And this is, of course, what makes this section here effectively an achromat, imaging all electrons or transporting all electrons from here to here, but preserving the bunch structure. So that explains the achromat. Now, 6 bands, I have already mentioned the 6 bending magnets, which are in place. And the hybrid refers to another nice trick that was developed also by Pantaleo Raimondi and first implemented at the ESRF EBS. This is the dispersion bump, which is needed at high energy machines to actually bring the refocus the electrons in energy space, basically make it an achromat, simply because if the dispersion is not high enough, you need excessively strong sextupoles to do this chromatic correction, and this is a trick to allow to do this in a feasible manner. And so this combination here, although looking quite complicated, has I mean a very delicate design. And of course I should mention to do that, besides the bending magnets, you need all kinds of focusing magnets. Those are those in other colors here. Both quadrupoles, sextupoles, and higher order multipoles are needed to actually achieve this refocusing. Now, what does this have to do now with the emittance? How do we get the emittance down? So for that, maybe just a reminder, the emittance is the product of the source size and the source divergence. And the electronic emittance would basically show you where these be a product of the distribution of where the electrons point, the transverse momentum versus the transverse size. And this is a conserved quantity around the ring. So that is basically the same at all the beamlines. And it's a property of the storage ring. And so how do we get to low emittance? And the rule of thumb is you should make as smooth a turn around the ring as possible, introducing as many bends that are possible. So thus the 6 bends. And so if you look at a 6-band achromat, this is has 6 bends rather than 2 bends as we have at PETRA III. So this makes a factor 3. And if you now look at this relationship, we find that we would expect 27 times lower bare emittance from this lattice as it is. And this means going down horizontally from 1300 to about 50 picometer radian. And indeed, this is a part of this design, but it shows you that this is not enough to go beyond and go to the 20 picometer level. So the next step is to reduce the emittance further by damping. And this works the following way. Suppose you have an electron that is kind of off axis, and you put it in a wiggler, then it will radiate into this certain direction, and by that lose a certain amount of its energy. Now, as it goes around, the RF is re-accelerating this electron, but the point is that this acceleration goes along the optical axis, and thus in the sum basically tilts the electron beam towards the optical axis and refocuses it. And this is the gain that is done by the damping. And of course, all put together, this makes it possible to drop then to the 20 picometer radiant. Now, if you look at this figure here again, one, of course, important question is, so what is now the resulting source size? And the source size, indeed, it depends on the amount of focusing that is possible in the straight sections. And this is measured by these beta functions here. And you can see that this is here basically defining the source size, as the source size is the square root of the emittance and the beta function. And so by that, you can actually calculate the source size. The point that I want to make is that indeed there is an optimal source size for highest brightness. And this optimal source size is given when the electrons basically are in a location such that the divergence is also small. Because if you look at the emittance, you can either do it with a very, very small source and a relatively large divergence, or a relatively small divergence and a relatively large source, and you could still have the same emittance. What you want to do is you have the right balance between both divergence and source size, and this is given as a rule of thumb if the undulator length, if beta is about undulator length divided by pi. Now this would be the optimum. Now if you look at this here, the beta function is slightly larger than 2, so it's more or less half the undulator length. So we're not perfectly on this spot, but among all sources around the world, this is really coming the closest to this optimum, and actually there is not too much gain if one could improve that. Now I should mention getting these beta functions to a certain point is not something where you just crank numbers. This is really something very delicate, and so we are very, very happy that with this new design the beta functions could be reduced and put to the spot in exactly the way that we need it, basically. So this leaves us with these parameters here, just to give you an idea. So of course the beam now for photon scientists in full width half maximum, the source size will be about 15 by 7 microns, and the divergence will still be extremely low, so that at a distance of 100 meters you will about have a 0.7 by 0.3 millimeter beam. Now this beam size is still convolved with an energy dependent size of this emission cone, but this is at the same order of magnitude, so the beams will not be much bigger than that. So this shows you that indeed now we can dive into the numbers and see that we have significant gains. I'll show you the brightnesses in just a second. Here's just a summary of all these things. And so basically we will have a brightness mode and a timing mode, very similar to what is available at PETRA III. And you see here the 40 bunch mode is still in brackets because it's still under investigation, but 80 bunch is set, and I guess it's a matter of the current that can be, where the 40 bunches that can be delivered. This is the main issue. Now, if you look at now well, of course, here are listed all the numbers. The important numbers are the horizontal and vertical emittances. And you see this is what makes the great difference to PETRA III. So here we have this gain, and I'll show you this enormous gain in brightness that results from that. Besides that, bunch lengths for timing experiments remains more or less the same. You see in timing mode, it's getting slightly longer because the bunches are so full, but nevertheless, one will be able to have relatively short bunches. And otherwise, one important issue is that the lifetimes are significantly higher than in the previous design, and also compared to what we have at PETRA III today. So indeed, also in terms of stability, this machine will be really superior. Now, in terms of brightness, indeed, if you plug in the numbers, enormous gains can be reached. in particular in the high energy X-ray range, around 10 kilo electron volts, almost 3 orders of magnitude. At higher energies, more than 3 orders of magnitude can actually be achieved. And that means basically the brightness at 100 kilo electron volts at PETRA 4 will be higher than at 10 kilo electron volts at PETRA 3 today. So this is, of course, extremely great news for users. This has to be built. And of course, parallel to all these considerations is the engineering integration happening already, the design of all the components. You see that these designs are finalized. The engineering integration is on the way. And of course, we currently virtually put together the storage ring in the CAD model to make sure that it all fits together. And of course, this is still work ongoing, but great progress has been made in this field over the last year. Now, and this is documented in these nice comments by the Technical Advisory Committee, which looks very carefully at this project, and they were really impressed by putting together the basis for such a major design change. That's the one that I just mentioned in such a short time. And it is, as I said, indeed acknowledged that this new lattice design has a superior performance, and is thus also strongly supported by the Technical Advisory Committee. So, and again, here I want to say from the photon science part, special thanks to the Accelerator Division for this really great work, because this is, of course, what we will most profit from in the future then. So, coming so in conclusion, I've already mentioned all these nice advantages. I will not repeat them again. So now I hope you can see why this is now, why it was possible now to get this going, and we have these nice possibilities now at the facility. All right, so let's jump across the tunnel wall into the experimental hall and look at the beamline portfolio. And so this was a major activity over the last year as well, with many contributors. And I would want to thank all the people that were involved here, and in particular also our review committees for spending a lot of time with us discussing and developing this first, basically, overall beamline portfolio design that we have at the current stage. And so basically, of course, now when we have this nice machine, we have to make use of it the best possible way. So the mission statement basically for the beamline portfolio is to make major contributions to solving the grand challenges that I mentioned earlier, but of course make best use of PETRA 4 to really achieve the best what is possible. Devise upgrades that will enable to really push these parameters to the limits and make make use of this world-leading performance that will be available at this new facility. Of course, we want to take leadership in many fields in hard X-ray science, but on the other hand, of course, one needs to make sure that we have a balance that basically all the experiments, or many experiments that are needed by the user community, can be done. And so we will have a nice mixture of high brightness experiments, but also high throughput techniques that are also needed in many contexts. And of course, so this is the cartoonish view of going from a really broad source to this really point-like source with very little divergence, shown below here again. So this all started, so the idea was to ask the community and actually get a survey or a good insight into what the user community really needs. And for that, now almost 2 years ago, we started the scientific instrument proposals call. where we asked the user community to propose scientific instruments to solve their questions, and basically stating their requirements and their dreams and wishes, if you like. Then by that, identify potential new experiments, particular instrumentation for PETRA IV, and of course, look for best ideas. I mean, survey the needs of the user community, and then, of course, based on that, make a user-tailored beamline portfolio. And of course, this was accompanied by many user workshops. I hope, and I know many of you attended those, and there were lively discussions, and in particular, people found each other to propose these scientific instruments. And of course, based on those, the beamline portfolio was developed. And so if you look back in time, we had a call for these scientific instrument proposals last year. The deadline then for submission was in December. We then, of course, looked at all these scientific instrumentation proposals in a technical review, had it peer reviewed, not to basically kick out scientific instrumentation proposals, but to get a ranking, if you like, a rating, and also get improvement, ideas for improvements to actually, constructively work with all these ideas that were put forward. And then the team that I just showed, they put together a draft beamline portfolio that was discussed with our Photon Science Committee during the March meeting last year. And so just to give you an overview, so over the scientific instrumentation proposals, you see that, again, the user community is really nicely reflected in these things, because if you looked at the picture of that Oliver showed earlier, you see this pretty much is what we have. This pie chart very much reflects our user community in what we have today, and so that is, of course, very positive. And many people contributed to all fields of science, and of course there are some proposals that address more than one field. So we had really a very nice outcome of this. And then, of course, I would like to thank you for that again very much, for all this, for all these this input. And of course, we try to exploit these things as much as possible to come up with the new beamlines for the future. So basically, at that time, we took these scientific instrument proposals and put forward worked out a few beamline profiles. These were 37 at the time, and they were basically scrutinized by our Photon Science Committee and looked at. They were basically developed from to make sure to have the complementarity of techniques for the different user communities and science cases, make use of synergies, take into account the size of user communities, the productivity of the user communities, and so forth, of course, and making sure that all these high throughput standard experiments are available, and many multimodal approaches. And so this was then the outcome of this review was further refined, and as Edgar already mentioned, we had in September a beamline portfolio users workshop. If you attended, of course, you recognize all kinds of things since then. So there we presented a realistic size beamline portfolio. And then had it, of course, reviewed officially by a review committee in November. And what I'm showing today is, of course, now the updated version of what already includes the outcome of this review to further optimize the beamline portfolio. And so from now on, basically we start with the beamline technical design, but of course also take new developments into account. I will mention that in a minute. So in the end, we came up now with 27 insertion device beamlines plus 1 VOV beamline. You heard of this. This is the successor then of the SuperLumi. With the current storage ring design, we will have 6 to 8 open ID slots for future developments. But also, I would mention there are some additional ideas to the beamlines that are shown here, which will be somehow, of course, put into the overall strategy. But there is still ongoing work. So, in particular, I'd like to mention here, for example, the imaging instrument of KIT, which it does not show up here, but which is, of course, set to play an important part also in the imaging in the future. So what were the criteria for prioritization? Of course, again, the scientific relevance and, of course, making use of the capabilities of the new machine. Basically the size of the user community and the productivity. Of course, the balanced representation of different techniques, fields of science and user community. And of course, we want to be able to adapt to future scientific developments quickly. If you recall, some time ago, we were discussing so-called flagship beamlines, and at the time, this name was attached to being at one of these long ID sections in the storage ring, and now with the new lattice and this nice and small beta function in the normal arc sections, the difference in brightness between these long straights and the shortest has diminished. That that is no longer necessary to really go to the forefront in brightness at one of these long straight sections. And so we've basically alleviated this criterion and basically think of flagships now in terms of ambassadors towards an example, beamline applications that feature the main features what PETRA IV can do. And so this includes, of course, they have to have a strong scientific case, groundbreaking instrumentation that is basically going beyond everything that is available elsewhere. And of course, we want to have it strategically in line with what DESY is planning in terms of the scientific development and this science city here on the campus Badenfeld. So with that ambassador character, of course, we will foster or kind of prioritize these beamlines in some way. But I guess you should keep in mind these are showcase. The flagships basically are now showcases that should showcase the capabilities of PETRA IV. So this is the beamline portfolio as we have it, and okay, I need to make sure that I get through this. So of course, I mean, these are quite a few beamlines, and it takes quite a time to really look at them in detail. You see that we have put them into certain villages here concerning basic techniques. And so I'm quickly going through all these different villages and show you what has been done there. But of course, if you're interested in the details, you might want to ask your colleagues at the beamline or contact us directly from the project, and we will then help you with your question, or maybe you have a suggestion and so forth. So coming to the point that PETRA is a microscope, there is one interesting observation that you can make. that many beamlines actually include imaging capabilities. So measuring something as a function of space and time is something that is really also nicely reflected here. And basically all techniques somehow become spatially resolved with this new machine. And this is, of course, one of the great advantages that this has. We aim for highest resolution, sensitivity, and of course field of view in the scanning microscopies under the working conditions. That we can use all these different analytical contrasts, often in combination. And of course, there is the possibility for full automation and basically, open multimodal scanning microscopy to industry, for example, to systematic studies. Many things of these, what today is like a really spearhead application can then become something really normal. And of course, then become very useful for systematic studies and in industrial applications. And of course, now this is complemented by full field microscopies of all kinds in all fields of science, looking at also at engineering materials for sustainable things, but also, of course, for in life science and so forth. So, looking at imaging, at the imaging part, you see, we call this the imaging village, but of course there are many other imaging beamlines or beamlines that do imaging. Just looking at this particular village, because it focuses really on the key strengths of PETRA IV, push the limits of timescales in correlation spectroscopies. This is basically the successor of beamline P10, which will allow us to really go with the correlation spectroscopies to timescales that are really interesting, for example, as for dynamics in aqueous solutions and so on. This will open up all the chemistry, the dynamics in biological systems also on small length scales, but also, of course, corrosion and all kinds of fields of science. We aim for highest resolution, sensitivity, and field of view in the scanning microscopies. Use the different contrasts that come about. Do a full automation, as I mentioned, and of course, full field techniques. And the science case is really huge. This is really cross topic, if you like, and therefore I